Hello, everyone. In the last lecture, we talked about the bias variance trade-off with an example of linear regression. So we mentioned that if your hypothesis class is too powerful, just means you contained too many hypotheses in your hypothesis class. Then it's likely that you have high variance and low bias. Just like a linear regression model, you have a high order polynomial and then the order is very high, so the n is large. Or maybe I say the dimension is large. On the other hand, if the hypothesis class is too restricted, just means you have very few hypotheses you can have in your hypothesis class, then like it's typically like D is very small, then you are likely to have low variance because you have very few functions in your hypothesis class. So every time you will get the same function, but it has high variance, high bias. Okay. And we can roughly plot the trade-off like this. So this is your size of your hypothesis, or how powerful is your hypothesis. And if your hypothesis is more and more powerful, then this is the variance. Your variance increases. And this is your bias decreases. But in extreme case, neither is good, okay? So you would like to seek some sweet point, which is here, okay, or somewhere here, that maintain the low variance as well as the low bias. So in this lecture, we are going to talk about regularization. So regularization is just a way of restricting your hypothesis class, but in a clever way. Okay. So the main idea of regularization is to restrict the hypothesis class. Okay. And we mentioned that in machine learning, you have to state your hypothesis class first, okay? And then you fit your data. And such hypothesis class need not to be any linear function or any affine function. You can restrict your hypothesis class in a clever way such that it considers many features, but not as flexible as it could have been, okay? So example, suppose x1, x2, up to xd are the features that may be related to the task. Okay, so they may be related to the task. So may or may not. Some features are related, some features are not related. Some features are more related than the other features, but you don't know. Okay, so our first attempt in previous lectures is it's all affine functions or all linear functions. Okay, just like the hypothesis is h of x is w transpose x. It's in the extended space. W is r to the d plus 1. Okay. So in this case, you know, if you have 100 features, but you only have 1,000 samples, it may not be good, okay? But if you have millions of features, but you only have thousands of samples, it's even worse, right? So this is our first attempt. We have no assumption except that it's a linear transformation or it's an affine transformation. My second attempt is maybe I somehow investigate the problem myself, or I do human learning, and eventually I know that x2, maybe x4, and xd are related to my task, and all other features are either unrelated or maybe it's negligible, okay? So my hypothesis class this time becomes, I'm still using an affine function, but this time it becomes maybe W2 x2 plus maybe W4 x4 plus xd wd, okay? Or maybe in a more general form, I just say W, maybe my feature I1 up to xi1 n, so I have n features in total, in, okay, where xi1 up to xin is the subset of all my features, okay? So I have these features in total. So this time I manually specify my features and I restrict my hypothesis class such that for the non-selective features, its weight must be 0, okay? So this is my second choice. And obviously you see some problem here. So maybe this feature, x1, is somehow related to the task, but not as much as x2. You either include it or you don't include it. If you don't include it, then it has no effect on the prediction, even if it contains some information, okay? But if you include it, maybe now you have included too many features and maybe your hypothesis class again becomes too powerful and now you have high variance. So this is my second attempt. Third attempt, okay. Now this time I'm having a clever idea. So I would like to include all the features, okay? I would like to include all the features, just like a linear transformation. But this time I would not allow my weights to be any point in the vector space, okay? The weight has to be some small numbers, okay? Just like if you fit a very high order polynomial, you get a function like this, right? So something maybe like this. Okay, something went drastically wrong here, okay, and here. But if you say my weight has to be small, then it's possible that you learn a function like this, okay? And if you learn a function like this, then, suppose your true function is something like this, then it's reasonably good, right, at this point. So the idea is I would like to restrict the values of the weight. It cannot be too large or it cannot be too negative, okay? The magnitude of the weight is restricted so that I still rule out a lot of hypotheses compared with attempt 1, but I include all the features in comparison to attempt 2, okay? So this time I would say W is still a D+1 dimensional vector, but I would require the norm of my W is less than or equal to a constant. Okay. This is exactly to say I cannot allow my weights to be too large. The values cannot be too large. So now we can consider different norms. Consider different norms. Okay. So let's give a definition of a norm. We focus on LP norm. The definition of a norm, suppose W is a vector space. It's in some vector space, okay, D+1 or D. Then the LP norm is defined as W1 plus W2 plus up to WD to the power of P, 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 and then 1 over P, okay? And when we have the plug-in P as 2, okay, L2 norm is, and this is the most common norm, so sometimes we omit the 2, okay? So, but I can also write 2 here, which is the square root of This time I don't have to have the absolute value because I take the square. And L1 norm is the absolute value of W1 plus the absolute value of W2, so on and so forth until the absolute value of WD. Okay. So the idea is, if suppose W L2 norm is 1, okay, then the points of W, so this is W1, this is W2, the points of W satisfying this constraint is on this circle, okay? And this point is 1, this is 1, minus 1, minus 1, okay? But if this is C, of course, this becomes C, C, minus C, minus C, okay? But I just assume it's 1. This is the L2 norm. A vector with L2 norm being 1 is a ball, with a radius of 1, okay? This is known as the unit ball of the norm, okay? And for P equals 1, so this L2 norm, L1 norm, then I'm saying the L1 norm, the size is 1, the vector length is 1, is equivalent to say, the different axes, the values of different axes sum to 1, okay? So it's just this diamond, okay? And this is 1, 1, minus 1, minus 1. It's also called uniball, although it's not a ball, it's not a ball in the L2 sense, but it's still the vectors that have the length of 1, okay, in the sense of L1 norm. So it's also called a uniball. Uniball just means the length is 1, okay? And likewise, we can compute, for example, maybe I have P greater than equal to 1, okay? P is greater than, I have P greater than 2, then you have a norm like this. But if P is larger, then this is closer to a square, okay? And if L is less than 1, then it's not a norm because it doesn't satisfy some of the constraints for norm. But the vectors have the unit length will be on this star, okay? And if P is smaller and smaller, then it's closer and closer to the axis, okay? And so this is not a norm. And in the extreme case, if P is infinity, then the unit ball is the square. And if P is 0, okay, then it's just counting how many axes is non-zero, okay? Okay. So we will focus on L2 norm and L1 norm. So the circle or the diamond is the point has a unit length, okay? But if I say L2 norm of a vector is less than or equal to C, and this is also less than or equal to C, then I'm saying all the points within this circle, including the boundary if it's less than or equal to C, are my valid points, okay, my feasible set. So this is known as my feasible set because it satisfies my constraint, okay. So I'm saying my weights has to be smaller, or the norm of the weights has to be smaller or equal to a constant, which is C, okay. And you can choose different norms. So in other words, our linear regression problem becomes I'm still minimizing subject to the weight of my W is less than or equal to C for some C. Okay. C is a constant. Okay, and this can be L2 norm. And if L2 norm is less than or equal to C, I can say the square of L2 norm is less than or equal to C square, and I can rebrand C square as C. Okay, so I just put a square here. It doesn't change anything. So this is the L2 penalized mean square error. Okay, and similarly, we can have the L1 penalized mean square error, which is minimized. Okay, C is also a constant. And this time I'm not taking the square because L1 norm, if you take the square, it's inconvenient, right? But if you take the L2 norm square, then you cancel out the square root, then it's convenient. Okay, so I don't have the square. And pictorially, let's assume this is my loss. W1, W2, and this is the contour of my loss, okay? Just means for this point, the loss is greater than this point, who is greater than this point, and the minimum loss is this, okay? So the most inner contour gives you the least loss. Okay. So I think I can copy it again. So L2 norm says my weight is restricted in this ball, okay? So suppose this is my ball. And now this optimization problem becomes a constraint optimization, say, I'm asking my weights to be within my feasible set, which means my size of the norm, the length of the norm is less than or equal to C, okay? Or square root of C, it doesn't matter. So square root of C. For some constant. Then I'm saying all the points here are my feasible set, okay? So all the points here are valid and you can choose your point. And if you have a point here, then I have a hypothesis function. If you have another point here, I have another hypothesis function. If you have a point here, then it's not in my hypothesis class, okay? So now I would like to choose the point within this feasible set such that it minimizes my loss function going to the most inner part of the contour, okay? Then which point? Probably this point, right? So this point cuts the contour most, okay? It's closest to the center of the contour. So this point gives you the best point, right? So the solution will be W star will be here, okay? Likely. If I have L1 norm, then my restriction is a diamond, okay? That's too ugly. And again, I will seek the points within this feasible solution, including the boundary, such that it minimizes my loss, which is saying it's the best to be closer to the center of the contour, right? Which point would be the optimal solution? Maybe still this point, right? Because you have a contour here, then it cuts this contour, then this point cuts the contour most. Okay, so this is my solution, L star for the L2 for the L1 norm, and this is for the L2 norm, okay? So now it looks like they are similar, right? You are restricting the vector length of your solution, and one is restricting the L2 length, L2 norm, which is the ball, gives you the ball, and the other is restricting the L1 norm, which gives you a diamond. But sometimes they can be very different. And here's the example. So what if my contour looks like this? Okay, so maybe my contour looks like this, okay? And this is the most inner point of the contour, but I'm just drawing part of my contour. So I would like to copy it once again for the L2 norm and L1 norm. And again, my, so maybe I can draw it closer. Okay. Again, my feasible set is this set, okay? For the L2 case, my feasible set is a ball. For the L1 case, my feasible set is the diamond. Okay. So now what happens? So in this case, you probably get this point, right? This point is all the points in this circle, within this circle that is closest to the optimum solution, okay? But for the L1 case, maybe your solution is this point, okay? It's the closest to here. They also look similar, but they are very different. Because in this case, you see this is W1, this is W2. W1 is exactly 0, and you only have weights for W2, okay? So this is something known as sparsity. Sparsity just means a large portion of the values are 0, okay? So if you have W1, W2, maybe one of them is 0. But if you have W1, W2 until W a million, then maybe most of them are 0. You only have very few weights that are non-zero, okay? So sparsity is not a mathematical definition because I cannot say how large does it mean by a large number of values are 0. So maybe 90% or maybe sometimes 99% if you are doing the genotype, you have many genes. So it's really sparse, okay? But the important idea of sparsity is that the value must be exactly 0. It cannot be a small number like 0.001, okay? Or minus 0.002. It's not 0, then it's not sparse. So in this case, you may learn some weight small, but it's not sparse because it's not exact 0. But in this case, this point is exactly 0, you see? So this is known as a sparse solution. And the reason why we care so much about whether this is exactly 0 or not exactly 0 is because if you have some small noise, such effect may be additive, can add up, okay, if you have too many features. Just like if you have a million of features, okay, then, or if it's exactly 0, so I have 1,000,001 features, okay, 1,000,001 features. If the values, for a million is exactly 0 and you have the weights for the last feature, okay, so I call it W0 or maybe W1, okay, but others are exactly 0, then you can just ignore these 1,000,000 features, right? They have no effect. But if your weight is not exactly 0, maybe I say my weight is 0.001, okay, for any I, the weight, the absolute value of the weight is less than 0.001. Then, if you sum over your features, I from 1 to 1,000,000, okay, Wi times feature I, okay, plus the last feature, okay, I call it W, maybe I call it 0, okay. Then this term has a huge effect in the final result, right? Because this term is very large. So that's why we care so much about whether the solution is precisely 0 or not. But how many features are exactly 0, it really depends on the task and data set. Okay, if you have larger data set, maybe I can have more features. But if you have very few samples with millions of features, then maybe you can select maybe very few features like 10 or a handful of features, right? So this is a very important idea of sparsity. And that really helps you to solve the problem that you have more features than samples, right? So I mentioned if you do the pseudo inverse, it gives you the result which has the minimum norm of the weights, okay? But if it's not sparse, then if you have too many features, this term can add up, okay? And your prediction is not generalizable. Your prediction has a very high variance. But if your values are exactly 0 for a large number of weights, then it's fine. It has no effect. Here is a further explanation of why L2 norm may not give you a sparse solution, but L1 norm is likely to be sparse. Okay. So think of my hand, especially the back of my hand, as a contour. So a contour is a layer of curves, right? And the most inner point is the optimum. And the outer point just means it's not so good. And think of, I have a few objects, okay? I have a few objects. So the points within this object, okay, is my feasible set, just like the ball of the L2 norm or the ball of the L1 norm. And now I would look for a point that cuts my contour most. And then if your object is smooth, okay, it's very smooth, the contact point of this object with my back of hand is pretty arbitrary, right? It's pretty arbitrary, highly depends on what is your task and what is your data. And then it's highly unlikely that you will get some point whose axis, some of the axes are 0, okay? It's highly unlikely, right? And even if you have this, this point may be the axis, right? But it's still smooth here. So if you use a hand to touch your object, it's likely that you don't get here. You don't get exactly on the axis. So it's not sparse. But think of, you have a sharp object, okay? You have a sharp object. So it's dangerous, don't do that yourself. But think of, this is my L1 norm, or this is my feasible set, okay? All the points within this object is my feasible set. And now I use the back of my hand to touch this object. Then it's very likely that you will get this point, right? So you try another object to touch it. If I touch it blind, okay, it's very dangerous, but you see, it's very likely that you'll get this point. But we notice that the sharp point, think of the L1 norm, the diamond, the sharp point or the sharp edges or the sharp angle is precisely on some axis, and you have some values being 0, okay? But this is not guaranteed. And sometimes you get, if your contour is this, then, you don't get this point, and this is not sparse. But think of, you are doing a high dimensional case, you have more and more sharp points, you have more and more sharp edges. If you use your hand to touch this object, then it's very likely that you'll get some sparse solution. And how sparse it is really depends on your constraint, what is your object, okay? And what is your loss, which also depends on the data set. Okay, having a sense of what the regularization is about, we're going to solve the problem. So essentially, we're going to minimize still the mean square error, which is over W. Okay, but now this time we have a constraint. So I say subject to the norm of my W is less than or equal to C. Okay, if it's L2 norm, I have the square. If it's the L1 norm, I just have the L1 norm, okay? Less than equal to. So they're the same. So there are two optimization problems. One is have the L2 norm constraint. The other is have the L1 norm constraint. Without theoretical justifications, they cannot be easily done by closed form solutions or by gradient-based methods because you don't know how to deal with the constraint here, okay? But in fact, we will show that under certain circumstances, the soft constraint and the hard constraint are equivalent. And we can make the hard constraint at some soft penalty. And then, you have a unified objective function in the unconstrained space. And then you can apply either the closed form solution or the gradient-based method to solve the problem. Okay, so that will be supported by the Slaters condition. We will not prove that condition, but we will state what is that. So let's think of a constraint optimization problem, which is minimize x, f naught of x, okay, subject to if I of x less than or equal to 0 for I from 1, maybe I have m, okay, I have m constraints. So this m is not a data sample. So I'm talking about generic optimization problem where I have inequality constraints and I have equality constraints and I call it P. I have P many equality constraints. I have M many inequality constraints. Okay. So this is a generic formulation of constraint optimization. And we talk about when we talk about a convex optimization, it's essentially saying optimizing a convex function on a convex set. Which says f, okay, 0 to f1 up to fm are convex functions. And h1 up to hp are affine functions, okay? So it basically says, suppose this is w x1, x2, and suppose this is my output, okay? It's f naught, okay? So it's actually a convex function, and you have some constraint of your x, okay? So maybe your feasible set is this, okay? Maybe your feasible set is something else. But when we talk about a convex function, the constraint must be a convex set. This is given by this inequality constraint with f being convex. Or maybe you have some equality constraints, then you cut this plate, x1, the input space, then this cut is an equality constraint, and it's be some affine functions. Okay, so convex optimization essentially saying I'm optimizing a convex function on a convex set. Then we consider the optimal value of f naught of x, okay, with the constraint, I'm saying p star is the mean over x, f0 of x, okay, subject to fi of x less than or equal to 0, hi of x is 0, okay? So this is my optimum value of my constraint optimization. So this is known as the primal problem, just means the original problem, okay, primal problem. Just means it's the original problem that we have. And we are going to define a dual problem where we use the Lagrange multiplier method. So the duality. We would like to introduce a Lagrangian. If you know the Lagrange multiplier method, it basically says every hot constraint is a soft penalty, okay? You would like to put the hot constraint as soft penalty. So I would say, define the Lagrangian, I call it L of x, okay? Lagrangian is a function of x, but it's also a function of some Lagrange multipliers. So I just leave it here, is f0 of x. And then for each of the constraints, you have a penalty, okay? So I have n many inequality constraints, so I have a penalty over n. So I call it I from 1 to n, fi of x. Then it's Lagrange multiplier method, right? So you have a coefficient for each of the penalties, so I call it lambda I plus p nu I f hi of x, okay? So for each equality or inequality constraints, I have a penalty, and for each of the penalty, it's given by a coefficient, like how severe it is if you violate this constraint, okay? So now Lagrangian is not only a function of x, but also a function of lambda and nu. They are both vectors, and of course, x is also a vector, okay? Because you have many lambdas and many nus. And later we'll know that the lambda has to be greater than or equal to 0. Lambda I is greater than or equal to 0 for every lambda I, which can also be written as more concisely, the lambda vector is greater than or equal to 0, which means every element is greater than or equal to 0, okay? Because I would like to have a constraint, fi less than or equal to something. Then if you say I violate the constraint, maybe my f is 3, okay? Then you have a penalty, it's a bad thing. And then you would like to eventually minimize the function, right? Then if lambda is maybe greater than or equal to 0, maybe 0.2, then you have an additive term of 0.6, okay? It's bad. It's worse than if you don't violate the constraint. So this helps you to memorize whether lambda should be greater than or equal to 0 or less than or equal to 0. It just means, it just says if you violate the constraint, then it's bad, okay? Okay, now I can define a Lagrange dual function which I denoted by g of lambda and nu, okay? It's the mean over x, Lagrangian of x lambda nu. I just eliminate the variable x. I assume lambda and nu are known, and I seek for the optimum value for x, okay? And then I eliminate x in the Lagrangian, but actually lambda and nu are unknown, so the Lagrange dual function is still a function of lambda and nu, okay? Which I can just write out by saying this is this. Okay, so now I can define a dual problem, okay? So I have a lot of definitions, but it's easy to remember. The dual problem is basically, I would like to have the optimum is to max of lambda and nu of my Lagrange dual function, where the lambda has to be greater than or equal to 0, as I mentioned here, but I have no constraints for nu. Okay, so the dual problem basically says I'm still optimizing the function, you see, I'm optimizing the function, but it's penalized by some self-penalty, so this is my first step. And the second step is I would like to maximize my Lagrange dual function based on my Lagrange multipliers, okay? It looks scary, but it's pretty standard. So there's a close relationship between D star and P star. They are very closely related. So first, weak duality. Okay, by saying the weak duality, I just mean that D star is less than or equal to P star, okay? This holds for any optimization problem, okay? Regardless of the convexity, regardless of the constraints, I mean, for any problem, the dual optimum is guaranteed to be less than or equal to the primal optimum. Okay, this is very easy to show. So I say for any lambda and nu, okay, I say, I'm taking the maximum, but I'm just showing for any lambda and nu, then g of my lambda is this function. Right, so this is just the definition of the Lagrange dual function. But I'm saying this is less than or equal to f0 x star plus X star, okay. So suppose X star is the optimum solution, optimum or the optimal solution for the primal problem, right? Because here I don't have any constraint. I'm taking the minimum of all kinds of X. Now here is a particular X, then the minimum is definitely less than or equal to one of the X, right? So it definitely holds. Then I know that, X star satisfies all constraints, okay? All equality constraints and inequality constraints. Then, h of I is 0, so this term just vanishes. If I of X is less than or equal to 0, okay? And lambda I mentioned, I have a convenient tool to remember lambda I. It has to be greater than or equal to 0. So this term must be less than or equal to 0, right? So I have a value subtracted by some number, then it's definitely less than or equal to the value, okay? Okay, where X star is the primal optimum solution. So this is exactly the D star or P star by definition. And I'm saying for all, then of course, if I take the maximum, then it still belongs to that. So, D star is less than or equal to that, okay? Okay, so this is the weak duality. It just says for any problem, for any optimization problem, the dual optimal value would be less than or equal to the primal optimum value. Okay, and this is sometimes known as the duality gap, or the gap between the primal and the dual, right? So what is more interesting is strong duality. Strong duality means that D star is exactly the P star, and with some X star being the optimum in both the primal problem and in the Lagrange dual function. Okay. So basically, a Slaters condition says if we have a convex optimization problem, and if it's strictly feasible, okay, if the optimization problem is convex and is strictly feasible, just means for any inequality constraint, it can hold without the equality, okay? It can hold strictly, so it just means exists some X such that f of I of X is strictly less than or equal to 0 for I from 1 up to M, okay? Then strong duality holds. Okay. So this theorem is not proved here, but you can read the reference yourself, but it's a very useful theorem and it's very easy to remember. The intuition is just saying, I have a convex optimization problem, which is strictly feasible. Then the hard penalty and the soft penalty are the same, because here it's the soft penalty, right? It's the soft penalty for some lambda, but the lambda is used to optimize, but there is some lambda there. And if you optimize this, it's the same as saying I'm optimizing the primal problem, okay? So when translating the result to my regularization, I have minimized subject to W square, okay, L2 norm less than or equal to C is equivalent to say I minimize. It's an inequality constraint, right? Minimize this. Okay. Some lambda okay. So just be careful. It's very confusing if you don't follow. Okay, what happens with my? Just be careful. It's very confusing that this F or this H must be 0, okay? It's not a constant like C. If it's a constant of C, then you should absorb the C into your function, okay? Otherwise, if you do linear regression, it's fine. But if you do a generic constraint optimization problem, it's likely that you make an error. Okay, you have to be very careful. F less than or equal to 0, and H is exactly 0. Okay, so you have this term. But indeed, I can omit this term because C is a constant and lambda is some constant, right? So I can indeed say this is minimized. Okay. If it's not for regularization, right, then you'd rather work out for C step by step, okay? Otherwise, it's very likely to make an error for some C, for some lambda. Greater than or equal to 0, okay? So now I have converted a hard constraint into a soft penalty, although I don't know what is the coefficient for that, but I know the coefficient is greater than or equal to 0. And actually, there's some correspondence between C and lambda, right? If you have a large C, then it means you have a weaker condition, then your lambda should be smaller, right? But if you have a small C, just means your constraint is very strict, then you have a very large penalty for that. But there's some correspondence, and may not be one-one correspondence. For example, this is my contour, and my feasible solution has already included the optimum. Okay, so this is my C. Then if you enlarge your C, the lambda is not changed. The lambda is just 0, okay? But in the usual case, it still makes a difference. So if it does not include the optimal solution, then it's likely that you will get different lambdas, okay? But the correspondence between lambda and C, it's usually hard to get the closed form solution, like how can I represent lambda in terms of C? But, it's not a problem because even if you work with this, you don't know what is C, right? You don't know what is C. C maybe 1, maybe 2, but I don't know. And in this case, I don't know lambda either, right? So you don't have to worry about the relationship, the exact relationship between lambda and C, but you can just determine lambda without any consideration of C, okay? And how can I determine what is the appropriate value for lambda? That will be similar to how to determine the learning rate. And I will explain this in future lectures. But for this moment, we know that if you have a hard constraint, it's equivalent to the soft constraint. And in both cases, you have some unknown constants to tune. And you don't have to tune the hard constraints. You just tune the coefficient for the soft constraint. Okay. And likewise, if you have the L1 norm, then it's the same. Okay. And I don't have to write this. And how to solve this problem should be easy, and that will be your homework. Okay, so you know how to solve the gradient descent. You know how to give a closed form solution if there is any closed form solution. So you just do it. Okay, that may be enough for this lecture. And in the next lecture, I'm going to talk about the max posteriori interpretation of this self-constraint. And also I'm going to tell how to tune different hyperparameters. See you next time.